Hello, and welcome back to another Orange Coast Mathematics video. In this video, we are going to start talking about trigonometric identities. You will notice that there are a variety of identities, and what an identity is a statement that is true for all values of x on which it's defined, meaning that it doesn't matter what you plug in for x, on one side, it will always be equal to the other side as long as you're not plugging in something outside of the domain of any of the functions. And these are very useful in Trig to be able to manipulate things into more useful forms depending on what you're doing. Now, these identities all have a derivation. We're not going to take the time to do them here. The derivations exist online. They exist in a Trig class, a full Trig class. But you can certainly talk to your professor if you're in a math class, or come to the Orange Coast College Math Center, and we can dive more deeply into where these come from. Some of them we already know, like cosine of x is the reciprocal of secant, but some of them might be a little bit newer, like these Pythagorean identities. But we're going to jump in straight into some examples to sort of see how these things work. So we've got a variety of examples, and let's talk about them a little bit here. In example 1, we are given that the cotangent of x is equal to 2/3, and we know that x is between pi and 3 pi over 2, which of course means we are in the third quadrant, and we're being asked to find the remaining 5 trigonometric functions. The way that I like to do this is to just draw a picture. I know that cotangent of x is equal to 2/3, which means that if I draw a angle here, remember cotangent of x is equal to the x value over the y value. So this x value must be 2, and the y value must be 3. Of course, we're in the third quadrant, so we are negative. Again, I know I'm in the third quadrant because it says x is between these values. So I'm asked to find the other 5 trig values of this angle. And we know to find the trig values, we just need to use the x, y, and r. Well, what is r in this problem? Let's use the Pythagorean theorem. We've got negative 2 squared plus negative 3 squared will be r squared by the Pythagorean theorem. That's 4 plus 9 is equal to r squared, or r squared is equal to 13, which means r is equal to the square root of 13. We have r always being a positive number. So now to finish off the problem, what do? Sine of x is going to be the opposite over the hypotenuse, which is going to be the negative 3 over the radical 13. If we want to rationalize that, we'll get negative 3 radical 13 over 13. The cosine of x is going to be the adjacent over the hypotenuse, which is going to be negative 2 over radical 13. If I rationalize this, I get negative 2 radical 13 over 13. The tangent of x is going to be, well, there's a couple different ways we can do it. We could say it's opposite over adjacent, or we could use the fact that it is the reciprocal of cotangent to say it must be 1 over this 2/3, which is 3/2. So you see there's a couple of different ways to do this problem. You could keep just using the definition, or you could use these identities. The cosecant of x we know is the reciprocal of sine. So we got, before we rationalized, we got that this was negative 3 over radical 13. So it's going to be 1 over negative 3 over radical 13, which is negative radical 13 over 3. And lastly, the secant of x will be the reciprocal of cosine. Well, cosine was negative 2 over radical 13, so this is going to be radical 13 over negative 2. So we see in that problem that we can use identities, not necessarily strictly needed. So we did a little bit of mix and match here. In this next example, though, we're going to rely on these identities more heavily. This problem asks you to simplify each expression. Now, simplifying is kind of an interesting topic. It's not always clear what is considered the most simple, but there's certain basic rules that we typically abide by. Like, you always want to combine like terms. You want to multiply things out. If you have a fraction that can be reduced, you want to do that. This problem further stipulates that we want to have our answer without quotients, meaning that we don't want to have things like sine over cosine in this problem. We would want to rewrite them as tangent, for example, using the identities from above. So the first thing I'm going to do in this problem is I'm going to rewrite this as cosecant is the same thing as 1 over sine of theta, and secant is 1 over cosine. A little bit easier sometimes to work with sines and cosines to see what exactly ends up canceling. I'm going to go ahead and do the distribution for this. If I distribute cosine through, I get cosine of negative theta over the sine of theta. Then I distribute it to this term, and I get plus cosine of negative theta over cosine of theta. Plus, distributing the sine over, I get sine of negative theta over the sine of theta, plus the sine of negative theta times the 1 over cosine theta gives me the sine of negative theta over the cosine of theta. Now, we can't go, there's a couple common mistakes students make. One thing I want to point out is that you can't do things like canceling these thetas. Those are inside of the trig function. It's not a multiplication you can cancel. So what we're wanting to do is we're going to want to, you also can't cancel these cosines right now because the inside is different. I've got a theta and a negative theta. So I'm going to go and use these negative angle identities to rewrite these a little bit. We know the sine of negative x is the same as the negative sine of x. We also know that cosine of negative x is just the same as cosine of x. You might consider looking at the graphs from a previous video to see why that might be true. So I'm going to say, well, what is this equal to? This is equal to cosine of negative theta really is just cosine of theta. Cosine of negative theta here is really just cosine of theta. Sine of theta here becomes negative sine of theta over sine of theta because of that negative. And this is minus sine of theta over cosine theta. Now we have one more simplification step. The problem said a couple of things. One is to simplify, so things like cosine over cosine we're going to want to reduce. It also said no quotients, that means no fractions. So this cosine over sine we're going to want to rewrite. Cosine over sine is the cotangent of theta. Cosine over cosine is 1. Sine over sine is minus 1 because of this negative. And the minus sign is minus tangent of theta. And we see here that that plus and minus 1 cancels. And so my final answer is just the cotangent of theta minus the tangent of theta. So it did simplify quite a bit. All right, moving on to the next problem. Let's do this in a different color to make it clear. In this problem, we have 1 plus tangent squared of theta over cosine of theta. And the first thing that jumps out in my mind is that 1 plus tangent squared. That's really making me think of an identity, a Pythagorean identity. And sure enough, I have it right here. 1 plus tangent squared of x is equal to the secant squared of x. So I can replace that 1 plus tangent squared with secant squared. So this is really equal to secant squared of theta over cosine theta. Of course, I know that secant squared is the same thing as secant is the reciprocal of cosine and vice versa. So I'm going to write this as the secant squared of theta times 1 over cosine of theta. But of course, cosine of theta is the same thing as just secant of theta. And therefore, I get this is secant cubed of theta. You'll notice we put the square sort of inside before the theta. That makes it clear that we're squaring the entire secant, not just the theta. So this is kind of a shorthand. It means the same thing as this. In this next set of examples, we're going to do what's called verifying an identity. Verifying an identity is a way of showing that an identity is true. So we're actually proving that this identity is valid. In other words, that the left side is always equal to the right side on the respective domains. And the way that we want to do that is we need to pick one side and manipulate it to make it look like the other. You can't do things like squaring both sides or adding 2 to both sides because that's assuming we already know this identity is true, and we don't. We're trying to prove it. So I'm going to pick one side to start with, and this is something that comes with practice, and we're going to practice it in future videos as well. But I'm going to start with one side and try to manipulate it to make it look like the other. Doesn't necessarily have to be the left-hand side. We could start with the right-hand side. I'm just picking the left-hand side in this particular problem. You'll find when you're doing these problems that they really can vary a lot in the way that you do them. You could potentially do a different manipulation and it still be correct using identities in a different order. As long as you're using just our fundamental identities from the start of this video and nothing else, you should be okay. So what am I going to do? I think the first thing I'm going to do, because I have no signs over here and I want to have signs in the end, I'm going to rewrite this in terms of sines and cosines. This cotangent squared is the same thing as the cosine squared of s over the sine squared of s. This cotangent is cosine over sine. All over, cosecant is the same thing as 1 over the sine squared of s. Well, multiplying by the reciprocal of this gives me what? The sine squared and the sine squared cancel, and I just get cosine squared of s. Now you might ask yourself at this point, wait, that's very simple. Shouldn't I just stop there? Well, if I ask you to simplify, then sure. But we're trying to show that this is equal to this right-hand side specifically. So what I'm going to do here, I'm recognizing that this is a difference of squares, and so maybe I want to utilize that square somehow. Well, going back to the Pythagorean identity, we know sine squared plus cosine squared is equal to 1. But what that means is that, just as some little scratch work, this isn't part of the problem. If I have that sine squared of x plus cosine squared of x is equal to 1, that means cosine squared of x is equal to 1 minus sine squared of x. So in this problem, I can write this as 1 minus sine squared of our variable is s. Well, that's fine because that is a difference of squares, and I can factor it using my a minus b, a plus b. 1 minus the sine of s times 1 plus the sine of s, which is exactly what we were looking for. All right, in this next problem, last one to go, we'll again pick one side to start with. It doesn't really matter which side. Sometimes one side's easier than the other. If it's not working one way, you should try it the other way. I'm going to start with secant of x minus cosine of x, just because I generally think it's easier to combine terms together than break them apart. Well, secant is the same thing as 1 over cosine of x, so I'll write it in this form. I know I ultimately want this to be one term, no minuses, so maybe we'll find a common denominator. I'll multiply this cosine of x by cosine of x over cosine of x. I do that because what I end up with is a fraction subtraction with a common denominator that allows me to rewrite this now as one fraction, 1 minus cosine squared of x over cosine of x. Oops, in this step I forgot the of x. It's important. Got to have something that you're plugging into cosine or it doesn't make sense. Okay, well 1 minus cosine squared is equal to, by the Pythagorean identity, just like cosine squared is 1 minus sine squared, if I had subtracted by cosine instead, sine squared would be 1 minus cosine squared. So I can rewrite this as just sine squared over cosine of x. Now, I know where I'm trying to go. I want to see this looking like a tangent times a sine. Well, if I write this as the sine of x over cosine of x times the sine of x, notice that's sine of x times sine of x is just sine squared. This is going to be what? Sine over cosine is tangent of x times sine of x. And oh, look at that. I have what I expected.